Let's look at one example about the system in time domain. Um, if we model a car bumper as mass spring damper, and if impulse testing results show the relationship impulse relationship between the x and t is in this data point like this. So the test engineer claim that the inertial effect of the bumper can be neglected, justify engineer claim. So this is a typical question to identify system model in time domain. So I have an impulse response showing this curve, looks like exponential. So supposedly based on the car bumper mass spring damper model, we should have, let's do a quick modeling. So kinetic diagram, free body diagram, kinetic diagram. So summation F equal to x double dot equal to. So this is a typical second order system model right here. It's second order system model, but the engineer claimed that the inertial effect of the bumper can be neglected. How do we justify this? Meaning inertial effect right here can be ignored or close to zero. Meaning this one will have this one right here, which is first order. In other words, this curve is a first order impulse response. So how do we justify this? If you say because it's exponential decay, that's why. Because this is exponential decay, there's no oscillations. So if you answer saying because no oscillations, so that's first order. Then that's not the correct answer. Why? Because this statement right here, no oscillation, is first order. Is a first order system from the response curve like this. This argument is this statement is very arguable. Why? Because it could be no oscillation, it could be first order, or it could be second order. Second order overdamp or critically damp. So if you will answer, your justification is because the response has no oscillation. That's why it's first order. It's first order. That's why the inertial effect can be ignored. So this is not correct statement because for second order system you can still have response without any oscillation, which is overdamped or critically damped. So how do we justify that? Okay, so let's take a look back of the first order response. One more time. First order impulse response. You can pull out the equation sheet. It should be A over tau E. So it's this. Okay, let's rework on these equations. Take a natural log x of t. So you can get natural log Ka over tau plus natural log E tau. So this term goes away, so we can put it in terms of minus 1 over tau t plus natural log K tau. So if we plot this one, natural log from the data point and t versus t, if you plot it, natural log x t, plot it, if the data point shows the curve, this is you plot natural log x versus t. If it give me this straight line or close to straight line, you can check the r squared value close to 1. If give you this straight line, that means this is the first order. So your justification for this problem or for the engineer's claim is you plot natural log x versus time to see if you can get the r squared values close to 1 when you set the equation y equal to mx plus b. And if the r squared value close to 1, meaning you do have a first order system response, impulse response. If this is the first order, this is the equations of this one. And then you can say this is first order system response. Then you can say it's first order. In other words, this term is neglected. So you can justify this engineer's claim that the inertial effect can be ignored